Hello.
Hello.
Yeah, you can hear me, right?
Yeah.
Okay. So we'll start with the problems that we had assigned for this particular class. So the first question was find the least positive integer, and that is a counter example, that one, right?
Yeah.
Okay. So the first problem is you have to find least n, that is a counter example to the statement if the sum of digits of a positive integer n of n is divisible by 27, then so is n. So you have to come up with an example of n that doesn't satisfy this, basically.
Yeah.
Okay, so what have you tried here?
Um, so I just started with like the smallest number that adds up to 27. So 999. That's like the smallest number that's gonna like add up to 27 when you add the digits. But then
How
that's
is that
divisible.
the smallest number?
Yeah. Well, because 999, like that'll add up to 27.
Okay,
But then the thing is, it's divisible by 27 because 27 times 37 is 999. So then I went to the next one, 1899, and that's not divisible by 27. So that's the counterexample.
right. So 1899 is the next higher number, which is n-
Yeah,
not divisible, which is basically sum of the digits is divisible by 27, right? Because it is 1899, yeah. So it is 27 sum of the digits. But 1899 is actually 9 times 211. If you think about it, if you divide by 9, you'll get 211 there.
right,
And 211 is no longer divisible by 3. So it cannot be divisible by 27.
right,
Okay, so the answer for this is 1899. The smallest n, that is a counter example.
right.
Okay, then the next question was about three-digit numbers with the property rate.
Yes.
How many three-digit numbers n have the following property? Three-digit numbers n with the property that the difference between n and the twice the sum of its digits, n minus twice of s of n, is divisible by 7. Is divisible by 7. You have to find how many such three-digit numbers are there.
Right.
Okay, so what have you tried here?
So I said that let's say n is like a number a, b, c. So then 100a plus 10b plus c minus twice of a plus b plus c is going to be some 7x because it's a multiple of 7. So then you get that 98a plus 8b minus c is a multiple of 7. And then 98a is already a multiple of 7 itself because 98 is divisible by 7. So then we have to get 8b minus c as a multiple of 7. And that'll happen if b is equal to c.
B
So
minus C has to be divisible by 7.
yeah.
So You can write it like this: 98A plus 7B plus B minus C, right?
Yeah.
This part is anyway divisible by 7. So you need to
Right.
make this divisible by 7, right?
Right.
So B minus C should be divisible by 7. So your options are B minus C could be 0 or 7, right?
Yeah.
B is equal to C is not the only possibility
Right. Yeah, yeah, yeah. So then
because
I got,
A, B, C are digits. So you can't have B minus C difference should be more than 7. That's not possible. 14 can't be the answer.
yeah.
But you can have B minus C could be 0, 7 or minus 7 also actually,
Yes.
right?
Yeah.
So if you have solved the question assuming just B minus C is 0, then you're missing out on some options.
Right. Yeah.
So how many did you get? You just assumed 0, right?
Yeah, so I got 90 options.
How many? 90.
Yeah.
Okay. So you said that B can be equal to C, then you will have A can be having 9 choices.
Yeah.
Wait, how is A having 9 choices? A can be anything.
But
1,
it can
2,
be 0.
9,
Yeah.
9. And what about B and C then?
They
Okay.
have 10 choices each.
So there is 90, but you
Yeah.
also have to now consider the cases, other cases.
Right.
So,
So then you're
okay.
adding up,
So let's take the case B minus C is 7.
yes.
So in that case, you will get B and C can be any, uh, can be basically 7, 0, 8, 1,
Yeah.
9, 2, right?
Yes.
And for the other case, minus 7, you'll get 0, 7, 1, 8, and 2, 9, right?
Right.
So there are cases where you are six different possibilities where you fixed B and C.
Yep.
And for each of these pairs, you'll get 9 choices for A, right?
Right.
So you'll do 6 into 9, no, 54 more.
Yes.
Because there's no restriction. You can do anything. 9 choices are there for each of these options of B and C.
Right. Yeah.
Answer is 90 plus 54.
So 144.
So everything is right except you have missed out on one or two cases, right?
Yes.
You have to see that it's not just B minus C is 0, it can be 7 or minus 7 also, right?
Right. Right. Yeah.
Okay. Third one was, I think, find the least positive integer such that that one,
Yeah.
least positive integer n such that the sum of digits of n, so let's say sum of digits of n and the sum of digits of n+1 are both divisible by 5.
Right.
Both divisible by 5. Okay. You have to find the smallest such number.
Yeah, I needed help on this one.
So, okay. So basically, we are getting that when we add 1 to n, what should happen is the sum of digits of the next number is divisible by 5 and the previous number also was divisible by 5, right?
Yeah.
So think about a number like this. If you have 1, 2, 3, I'm just making up a number and I'm thinking, what will happen if I add 1 to it? It will become 1, 2, 4, right?
Right.
This is a typical number where when you add 1, there is no carryover.
Yes.
If there is no carryover, here the sum of the digits is, if it is divisible by 5, for example, it would have been divisible by 5 if I had done 1 to 5, for example, right?
Right.
But the next digit is this. No, sum of the digits has to be divisible. It doesn't matter like this. Sum of the digits is actually 6. So I could have done 1 to 2 rather, right?
Yeah. Right.
If it is 1 to 2, sum of the digits is divisible by 5. But
Mm-hmm.
sum of the next digit is not going to be divisible by 5.
Right. Yeah.
So basically, in a situation where there is no carryover, this property is not going to be possible, right?
Right. Yeah.
So now what you have to think about is, if there are carryovers happening, then what will happen, right?
Yes.
So let's say there are k carryovers when you add 1. So basically, now we have to get a relationship between sum of the digits of n+1 and sum of the digits of n if there are k carryovers happening, right?
Right.
So, for example, let's say the last k digits. When will k carryovers happen? When you just add a 1. Carryover happens when you add a 1 if the last digit was 9, right?
Right.
Do you understand what I'm saying?
Yes.
If you add a 1 in a when you have a 9, then only you get a carryover, right?
Yeah.
So this is one carryover. If you want k carryovers, you should have last k digits as 9, right?
Yes.
Do you understand what I'm saying?
Yeah.
So let's say you have some k digits as 9 and last k digits. This is k times.
Yeah.
The remaining digits could be stuff that doesn't get carryover or not. So it could be any set of numbers here, right?
Right.
But it
Yeah.
should be such that when 1 is added, it doesn't carry over after that, right?
Yes.
Okay. So when you add 1 to it, you will get 0 here, then 0 here, then 0 here, then 0 here, and 1 gets added to this, right?
Right.
Whatever is the sum here, this sum is going to be just that number plus 1, right?
Yeah.
So notice that so many numbers disappeared from here, right? Became zeros.
Yes.
4 times 9 got converted into 0, right?
Mm-hmm. Right.
Do you understand what I'm saying?
Yes.
So, the difference between the number of digits here and the sum of the digits here and the sum of the digits in this number. Let's
R-
think about it. So, sum of the digits of n+1, and we are doing the case when there are k carryovers, right?
Yeah.
sum of the digits of n+1 is equal to sum of the digits of n minus 9k and
Right.
plus 1.
Yeah.
Do you understand?
Yes.
Because when 9k carryovers happened, then k times 9 got vanished, right? Became 0.
Yeah. Right.
So from the original number, we have to subtract 9k and you have to add 1, right?
Yeah.
Is it clear?
Yes.
Okay. Now, this is the equation that we have, and we want to ensure that both of this and this are divisible by 5 somehow. Correct?
Right.
Then only we can satisfy the problem.
Mm-hmm.
So basically, we can say that Sn minus S of n+1 is equal to 9k minus 1, right?
Yeah.
Okay.
Right.
So now we want to make this and this both divisible by 5. So this must be divisible by 5 then, right?
Right.
Correct.
Yeah.
So the smallest number here, if you put 1, you will not get something. 2, you will not get it. 3, you will not get it.
4.
4, you will get it, right?
Yeah.
That's the first time you are getting 9k minus 1 is divisible by 5, right?
Right. Yeah.
K is smallest is 4, right?
Yes.
Which means 4 carryovers must happen at least,
Right.
right?
Yes.
So then in these conditions, we'll have to have 4 nines at the end, right?
Yes.
And some digit here. So at least it should be 5-digit number, right?
Mm-hmm.
You could
Right.
have more digits also, but we want to make the smallest number. So let's take only 1 digit after that, right?
Yeah.
But we need to ensure that the original number here is also divisible by 5. And after you add 1, it's also divisible by 5, right?
Yeah.
That is the condition of the problem, right?
Yes.
So original number is divisible by 5. The sum here is 36. To make it divisible by 5, the sum of the digits of the original number, we need to put a 4 here, right?
Right.
The smallest way to do that is to put a 4. You can put a 9 also, right? Do you understand what I'm saying right now?
Yes.
The question is saying that the sum of the digits of the original number is divisible by 5, and the sum of the digits of the original number plus 1 is also divisible by 5.
Yeah.
So the smallest way to get a divisibility here is to put a 4 plus 1 will make it 5, 0, 0, 0, 0, right?
Yep.
So you can see that both of these numbers, the sum of the digits is divisible by 5, right?
Right.
Do you
Right.
understand what we have done so far?
Yes.
If you take a number where there is no carryover happens, then this is not possible only.
Right. Yeah.
That both the initial and final number, sum of the digits can be divisible by 5. It's not going to be working.
Right.
So you have to ensure some carryover. And whenever you do carryover, you have to realize that since you are adding just 1 and some terms are going to change, 9 is going to become a 0 and all, right?
Yeah.
So we are able to figure out this condition if there are k carryovers, right?
Yes.
And then since we need the smallest possible number, we are looking at low values of k for which it is divisible by 5, which gave us k is 4, right?
Right. Yes.
Is it clear what we have done?
Yes.
Okay. The next problem is about nice numbers. And the definition of nice numbers was that it should have distinct digits, and they should be such that the digits can be divided into two groups, can be divided into two groups where the sum of the digits in each group is the same,
Yeah.
where the sum of digits in each group is the same. The example that was given was the number 67890. Notice that all the digits are distinct and the digits can be divided into groups of 6 plus 9, which is equal to 7 plus 8 plus 0.
Right.
The question was, can we have two consecutive 5-digit numbers which are nice? Two consecutive 5-digit numbers which are nice. Okay. Did you get something here?
Um, yeah. So what I did is it says that two consecutive 5-digit numbers, both of them have to be nice. But the thing is, if they're consecutive, one of them is just going to add one to the other. So then I said that one of them has to like carry over. So the last digit should be 9, and then the next number's last digit would be like 0 because you're carrying it over. And then I just experimented a bit and I got like numbers like 15310 and 15309 as like two consecutive 5-digit numbers, which are nice. And then like 24309 and 24310, stuff like that. Yeah.
How is this nice?
Because you can take 153 as one group and 0 and 9 as one group. And
What
then the
about the
second
next one?
you can take 5 and 0 as one group and then 113 as another.
But there is repetition here. No, it's not fitting.
Oh, it has to have distinct digits. Oh, okay, then 24309 and then 24310. That's another pair I got.
Mhm. Okay, so you are getting one pair at least.
Yeah.
Okay, so this seems to work. Uh, okay, so the point is that again here there should be some type of a carryover, right?
Yes.
So one thing to notice here, first of all, is that if n, which is our number, if n is nice, then sum of digits of n will be even. Why? Because there are two groups in it which have the same sum, right?
Yes.
So we need to look for some 5-digit number where sum of digits of n is even and sum
Yeah.
of digits of n plus 1 is also even, right?
Right.
nice number can be said that the sum of n should be even for it to be nice, right?
Yeah.
Okay. So if S of n and S of n plus 1 are both even, so then what you will realize is that the n should end with an odd number of nines. The reason is the odd number of carryovers should happen, 1 or 3 or 5. It should end with an odd number of nines. You can have four
Yeah.
digits here. So when you add a 1 to it, you get a 0 and this changes 1, right? Only one carryover happens here, right?
Yeah.
The rest of the three digits are unaffected. This digit will become a plus 1, right? Let's say the first three digits are unaffected, B, C, D. They are B, C, D, right?
Yes.
This is the new number. This is the old number, right?
Mm-hmm. Right.
So old number is sum of the digits here must be even. New number, if you think about it, sum of the digits is A plus B plus C plus D plus 1, right? And
Right.
here it was A plus B plus C plus D plus 9, right?
Yeah.
So if old number was such that it was nice, this sum was even, which means A plus B plus C plus D was odd, right?
Right.
So here also it is odd plus 1, so still even, right?
Yeah.
Do you understand what I'm saying?
Yes.
So if this was nice, this is guaranteed to be nice
Right.
because the sum of the digits here is even, which means this can be grouped into two parts which are equal.
Yeah.
So that means automatically A plus B plus C plus D is odd, and therefore automatically this is also going to work out. It is going to be nice,
Yeah.
right?
Yes.
Same thing you can test if there are two carryovers, it won't work. You can test that. For example, if I do BCD 9 9 and add a 1 to it, you get a 0, you get a 0, you get a D plus 1 and a B and a C, right?
Yeah.
If this number is nice, then first of all, it can't be nice because there are two repetitions,
Oh, right. Yeah.
right?
Yeah.
Uh, right. Like even apart from that, here the 9 plus 9 18, and then V plus C plus D is even. And now even plus 1 is odd here, right?
Yeah.
It won't work even apart from that, right?
Right.
But if you take odd number of nines, it will work, right?
Right.
Do you understand what I'm saying?
Yeah.
So basically, now you can just figure out some numbers which will fit this pattern. One of them you have figured out. Another number that was possible is 2, 3, 4, 8, 9. 2, 3, 4, 8, 9 will fit because when you add 1 to it, you'll get 2, 3, 4, 9, 0, right?
Yeah.
That also has all digits are different. Here also all digits were different, right? Notice that the sum of the digits here is 18, which is even, and the sum of the digits here was 5 plus 4, 9, 9, 18 plus 8, 26, which is also even.
Right.
So both of them are nice numbers
Yeah.
because they have different digits and even sum of the digits.
Right.
So the main thing to figure out here was, can you understand what a nice number is properly? Like one way to understand it is to say the sum of the digits of n will be even.
Yeah.
And if you can find one counterexample also, then we can answer whether can two consecutive five-digit numbers be nice. Our answer is yes.
Right.
Is it clear what I'm saying?
Yeah.
Okay. Uh, the next problem was, okay, find the greatest positive integer with distinct digits. Greatest positive integer with distinct digits such that the sum of any three of its digits, such that the sum of any three of its digits is different from 19. The three of its digits is different from 19, right?
Yeah.
Okay. So, did you try this?
Yes. So what I did is that since we have to find the greatest positive integer, I just started off with like the greatest three digits, so 987. That doesn't equal 19, so then I added a 6 to it, and still you can't take any three that equals 19. And then I kept on going down. If you add a 5, you get a 19 somewhere. 4, same thing. 3, same thing. 2, same thing. But if you add a 1, you can't get 19. And if you add a 0, you can't get 19 either. So the number is 987610.
How do you know this has six digits?
Oh, I didn't know. I just went like saw how many digits I could add on.
How do you know what you have selected is the greatest possible
Because
integer?
the numbers are ordered in like the largest possible way.
But the number of digits you have chosen is six only, right?
Yeah,
How
but you
can you
can't
not
repeat
make,
digits either.
huh?
But you can't repeat digits either.
So how can only, why can't it why not be nine digits or eight digits?
Because then you're gonna be able to choose three digits who have a sum of 19.
Your answer is wrong. You have to think again. There is a number which is bigger than what you have chosen.
Mm,
First, you have to realize how many ways you can make 19 using three digits. What are the ways that we have to make 90 using three digits?
uh, 199. Yeah.
199 is not a case we can consider because we have to have distinct digits.
Oh, right, right, right. So 649 or 568. Yeah. Then 649. Then 289.
Basically, you can have any two or at maximum two out of three, seven, and nine, and two out of five, six, and eight.
Yeah.
Maximum two digits out of three, seven, nine, Similarly, you can have maximum 2 digits out of 5, 6, and 8,
Yeah.
which means you are losing 2 digits here. The number will have at most 8 digits. You cannot select one out of these three, one out of these three. You are going to be left with 8 digits in the number
Yeah.
because there are 10 total digits. Now you can think of, you have to start by thinking of, can we make an 8 digit number which fits the conditions? The 8 digit number, you have to make the greatest possible 8 digit number. So let's say you are skipping the 9 here. You can try, but one of the options is to skip the 9 from here and skip the 8 from here, right?
Right.
And you start with making the biggest possible 8 digit number, because now that we have removed these, the highest sum of any 3 digits will be 7 plus 6 plus 5.
Right. Oh, so then that's
It is
18.
it's impossible to worry about it anything. There's no need to worry about anything now.
Right. Yeah.
You will get the number 76543210. This is the biggest possible such number.
Yes.
And there is no issue of any 3 digits being adding up to 19 here, right?
Yes.
You can try other options, but then you will have to worry about many cases. For example, if I use 9 and use 3, for example, and remove 7, and here
Yeah.
if I remove 6 and I'm using 8 and 5, then I have to worry about different cases, because 9 plus 8, now I can't use 2.
Right.
Then you are going to get stuck in different cases, right?
Yes.
Then when you try to make an 8 digit number now, there are many ways I think it can go wrong,
Right. Yeah.
because you can't make an 8 digit number now because 2 is not allowed. Similarly, right, 3 plus 5, 3, 9 plus 5, 14, 4 is not allowed if you use 9 and 5.
Yeah.
So technically now the number of possibilities is going to be very small numbers using these 4 digits, right? Maybe 5 digit number can be made with 1, maybe 6 digit number can be made with a 0, right?
Yeah.
Do you understand what I'm saying?
Yes.
If I use all these four, I can make 9, 8, 5, 3, and after that I have maybe 1 I can use, 0 I can use, 2 I can't use, right?
Yes.
4 I can't use. 6 can I use? 6, 6, 3.
No, because 6, 5, and 8 make 19.
Right. So maybe the maximum I can make is this number,
Yeah.
right?
Yes.
But this is much smaller than this 8 digit number that we have found here.
Right.
The way we made the 8 digit number is to realize that let's remove the problematic numbers like 9 and 8 first. Then I have left with 8 digits from 7 to 0. And
Right.
there is no issue of any 3 digits adding up to 19 now. Do you understand what I'm saying?
Yeah.
Okay, so that is your answer here. This is the biggest number. There was one more question, right?
Yeah. There was two more. 6 and 7.
Okay. What was question 6?
Find the least positive integer whose last digit is 1 and has the property that if the last digit is moved to the front, you get a number 3 times smaller than your initial number.
Last digit is 1, and if it is moved to the front, if 1 is moved to the front, new number is 3 times smaller than the initial number. Did you find a number like that?
No, I tried to, but then my number didn't work at the end because I got like 42851, but then that didn't work out. Because if you plug it back into the initial like thing, it doesn't work.
It's close, you have just missed out on it. Hmm. The answer is 428571.
428571. Uh oh, when I was doing division, like from 29999, I didn't add the 7 at the end. Oh, that was the mistake. Okay, yeah, I got it.
So basically, we are saying that let the initial number last digit is 1, right? So the
Yes.
remaining digits will be something here,
Yep.
and we can say that probably 1, this is moved to the front. Okay, so let's say this has n digits.
Yeah.
So if 1 is moved to the front, the new number is like this. And the new number is 3 times smaller than the initial. So 3 times of this should be equal to this, right? Correct?
Yeah.
So basically, initial number can be written as, right. So if you think of this group of numbers as one number, to make the initial number, you have to say it is 10n plus 1, right?
Yeah.
For example, you can say that 42857 into 10 plus 1 is this number, right?
Yes.
So you have to think of it like this. This is the n digit number part of it here. 10 times that plus 1 will be the initial number, right?
Right.
Here, on the other hand, you have an n digit number here and 1 is ahead here, right?
Right.
So we can say that this number can be written as 10 power n plus capital N. Why? Think about it. That's the same thing. 1 has been brought here. 1 and 42857. So technically it is 5 digits here. So you're getting 10 power 5 plus 42857, right?
Yeah, right.
Do you understand what I'm writing here?
Yes.
So our equation becomes 10n plus 1 is 3 times 10n power n plus capital N, right?
Yes.
And we can solve for capital N here. Capital N will become 3 into 10 power n minus 1 divided by 7 because 10n and 3n, right?
Yeah.
And obviously we know that this capital N is an integer, so the top part must be divisible by 7 somehow. right?
Yes.
The capital N here comes out as an integer. So that was
Right.
what we were calling it, n-digit number, right?
Yeah.
So this has to be divisible by 7. The smallest case will be when small n is 5. You can check all the smaller values of n. When you check 1, for example, you get 29, not doesn't work. When you check 2, you get 300 minus 1, 299, doesn't work, right?
Right.
When n is 5, it becomes 3 into 10 power 5 minus 1, which becomes 300,000 minus 1. So it becomes 299,999, right?
Yeah.
When you check the divisibility, you can see that it will be 4, then 1 9, so 2, then 5 9, so 8, then 3 9, then 5, and 4 9 and 7. See,
Yes.
it is divisible by 7, and after dividing by 7, you will get 42857.
Right. Yeah.
So when n is 5, capital N becomes 42857, right?
Right.
So our initial number is 42857 and 1.
Yes.
Do you understand?
Yeah.
Okay. So you had come close to it, but what did you do?
Oh, so when I was dividing the 29999,
You
I
got
just
till here.
yeah, I just divided it wrong. And I got 4285 instead of 42857.
Okay. Next problem is find all three-digit numbers. Find all three-digit numbers such that sum of digits of n is 3 times the sum of digits of n plus 3.
Right.
Sum of digits of n is equal to 3 times sum of digits of n plus 3.
Right.
And we have to make sure that this condition is true for three-digit numbers.
Yes.
Okay. Did you get
So,
any numbers like that?
yeah,
Which numbers?
like 108, 117, and 207.
Okay, that's correct. So, right. So the point here is that if your number n is like this A, B, C, right,
Yeah.
then it should satisfy 3 times sum of n plus 3 should be equal to S of n, right?
Yes.
So that means clearly S of n should be divisible by 3, right?
Yeah.
By just this equation, we know S of n is divisible by 3, right?
Right.
And if S of n is divisible by 3, then we also know that basically that means A plus B plus C is divisible by 3. Then if you add 3 to it, right, it
Hmm.
will still be divisible by 3, right?
Yeah.
So we can say that if S of n is divisible by 3, S of n plus 3 is also divisible by 3.
Right.
Right. So then if S of n plus 3 is also divisible by 3, then technically 3 times S of n plus 3 is divisible by 9, right?
Right.
Do you understand what I'm saying?
Yes.
So we are getting that S of n is divisible by 9, right?
Yes.
So then the ultimate value of S of n is less than equal to 27, right?
Yeah.
Because all three digits can be 999. Higher than that is not possible.
Right.
But 999 doesn't work in the problem because when you do 999 plus 3, it becomes a four digit numbers. number, right? And you
Yeah,
will not be able to satisfy this condition. It is 1002. The sum of digits here is 3 only, right?
right.
So 3 times 3 is not equal to sum of digits of 999, which is 27. Correct?
Yes.
So S of n is equal to 27 doesn't work. So it can be now 9 or 18, right?
Yeah.
Which are the two cases you are getting here? When you check 9 and 18, those are the situations that are possible. S of 18 is also impossible, I think. You're only getting the cases where S of n is 9.
Yeah.
You might have done it by a different way, but it's fine. The ultimate idea is the same thing. If you're getting the correct answer, then means you have got the correct idea, right?
Yeah.
Okay. Now, right. So now we have a few more questions here, and then we'll go to the next part, which is going to be theory of division algorithm and stuff. So what I will do is tell you these few more questions first. The first one is with the digits from 0 through 9, each digit being used exactly once, we form two 5-digit numbers, M and N. We have to find the largest M such that M is equal to 7 times N. That is the question. Then the next question is find all 5-digit numbers that are equal to 45 times the product of their digits. Product of their digits. Okay, that is the second one. Then the third problem is find the digits x not equal to 0, y, and z such that xyz, the number, we have put a bar on top. Xyz is equal to x factorial plus y factorial plus z factorial. The bar on top determines that it is a 3-digit number xyz.
Yeah.
So you have to find the digits such that this is possible. Have you written down this question? Okay, you have written
Yeah.
down first one for sure, right?
Yeah.
Okay. So fourth problem is find all positive integers n such that each digit of n square minus 3 is 3. Find all positive integers n such that each digit of n square minus 3 is 3. Uh, okay. Okay, that's about it. These 4 problems you need to try. Uh,
Okay.
if you're able to do them, or even if you're not, then we'll discuss the solutions and we'll go to basically the next theory item, which is division theorem and divisibility, the division algorithm. That's very important. That's going to teach us many things. So that is what we'll focus on from the next class onwards in number
Okay.
theory. I had sent a few documents. I thought did you get them for geometry?
Yeah, yeah, yeah.
So those 3 papers for the AMC 10 and all, you should
Yeah.
try the geometry problems there.
Yeah.
So that is what we'll cover in the next class, and
Okay.
after that we'll continue with number theory. Okay,
Okay.
fine. That's all for now. We'll see you next week.
All right. Thank you.
Hmm. Bye.
Bye.